Finite element analysis requires a precise mapping process, converting a continuous physical domain into a discrete system of solvable linear equations. When a problem expands into 2 dimensions, the bookkeeping required to track that space becomes significantly more complex. In a 1-dimensional line mesh, the relationship between local elements and global nodes is linear and predictable. Element 1 connects nodes 1 and 2. Element 2 connects 2 and 3. In a planar 2D mesh, that clean arithmetic sequence disappears. Geometric hardcoding is no longer viable because the topology no longer follows a single path. Take this standard 2-dimensional grid, for example. We have 12 total nodes defining 6 individual rectangular elements. If we look at an interior point like node 5, it connects outward in multiple directions, linking directly to nodes 2, 4, 6, and 8. Writing a program that relies on a fixed formula to determine these multidirectional connections is inefficient. The logic becomes difficult to manage if the mesh geometry or element count changes. Instead, solvers utilize a specific data structure known as a connectivity register. This register acts as a lookup table, explicitly mapping the local node indices of any individual element to their true global coordinates within the broader system. By utilizing a dynamic connectivity register, an FEA algorithm can process and map a mesh of any shape or size without needing to hardcode the geometry. Once the mesh is defined, we need a mathematical container for the entire system. This is the global stiffness matrix, or matrix A. The dimensions of matrix A are determined by the mesh. It is an n by n square matrix, where n is the total number of global nodes in the domain. For our sample 12-node mesh, the computer pre-allocates an empty 12 by 12 grid in memory. To populate this matrix, we pull data from the local stiffness matrices, matrix K, of each individual element. Solvers execute this population systematically using a nested loop architecture. The outer loop instructs the algorithm to iterate through every element, designated as I. For each element I, the loop fetches its local 4 by 4 matrix K. An inner loop then cycles through every local node, labeled J and M, within that specific local matrix. During this cycle, the algorithm consults the connectivity register to translate local J and M indices into global positions, K and N. This nested loop structure is a universal engine for matrix assembly. It functions independently of the specific physical equations being solved. We can apply this loop logic directly to element 5 from our sample mesh. This diagram illustrates where data from element 5 is placed inside the global matrix. Based on connectivity, it maps to global rows and columns 5, 6, 8, and 9. The core instruction is step 8, AKN equals AKN plus KJM. The left side of the equation, AKNN, is the target coordinate within the global matrix. The right side, KJM, is the calculated physical stiffness value being pulled from the local element. The critical component of this equation is the addition operator. The algorithm must accumulate the values. It adds the local value to whatever number is already stored in that global cell, rather than overwriting it. This accumulation mirrors the physical reality of a continuous mesh. When multiple elements share a single point, like node 5, their individual stiffness contributions physically add together at that joint. Without this overlapping addition, adjacent elements couldn't communicate forces. The mesh would behave as a collection of fractured pieces instead of a continuous solid. The loops repeat this process until every element in the domain has mapped its values into the global grid. Once the assembly is complete, the global matrix A stands as a complete mathematical analog for the physical properties of the unbroken domain. With the global system assembled, the solver moves to calculate the actual variables across the mesh. However, in a standard Laplace equation problem, we have a system where no physical constraints have been applied to the boundaries yet. This represents the unconstrained state of the global system. Notice the right-hand side of the equation. The entire system is currently set equal to a vector of zeros. Setting a homogeneous system of linear equations equal to 0 has an immediate mathematical consequence. This results in a trivial solution, where the solver computes every unknown interior variable, phi, as 0. At this stage, the assembled stiffness matrix represents the potential for physics. but it lacks the external data required to compute a specific state. To generate a non-zero solution, we must apply boundary conditions. This means taking known non-zero values, such as a specific temperature, and enforcing them onto outer global nodes. This creates an algebraic complication. Both the known boundary values and the unknown interior values are combined within the same column vector. Here, boundary knowns, F1 and F2, are stacked in the same vector as target unknowns, phi3 and phi4. To separate them, we use matrix partitioning. The solver slices the matrix horizontally, dividing the equation into two distinct sets. The first partitioned equation isolates rows associated with the known boundary variables, F1 and F2. The second partition isolates rows containing our unknowns, phi3 and phi4. With the equation split, the known boundary values can be multiplied through the stiffness matrix and moved to the right-hand side of the second equation. Because the right-hand side is now populated with non-zero values, the solver can compute the specific behavior of the interior variables. Matrix partitioning transforms a broad geometric description into a focused algebraic system, allowing for the calculation of the domain's interior physics.